Welcome to Lecture 3.1c. This is the last of the 3 lectures on Section 3.1. Now that you have your text, if you take a look, you'll notice that we've been through the first 2 pages. We've talked about how to define the derivative, and we did that actually using a limit definition, and we've talked about sketching the graph of the derivative function. The last thing is to talk about how we use a derivative when it comes to real-world data. And this is actually the most important, although in some ways it may seem less technically complicated. Derivatives are everywhere in the world around you, and they are in fact the only way to solve a lot of really important questions. But in order to see all the ways in which derivatives have shaped really everything that works around you, you need to be able to interpret a derivative given a real-world context. These 4 questions are the kinds of questions that I'm going to be asking in this video, and the kinds of questions that I expect you to be able to answer given a real-world situation. Let's look at our first example. This is an example about cooking. Go ahead and read the example out loud to yourself. Right, so seems simple enough. Well, let me ask you some questions. If we think of this situation as a function, what function are we talking about? Exactly. This is the function where you use time to predict temperature. Now, predict might not be the best word, but certainly if we set up a table like the one that Carlos would have written down, his x-axis or inputs are time and his y-axis or outputs are temperatures of the soup. Okay, so if I were to graph his data, what would it mean if there was a maximum? What would that maximum point represent? Exactly. The maximum point would represent the hottest that the soup ever gets, and presumably that's going to happen at some point. Now, what if we want to talk about the derivative of this function? What would the derivative represent? Great. So I often use units to help me understand derivatives. If I think about the units here, the original function is inputting temperature and outputting, it's inputting time and outputting temperature. So the derivative would be the change in temperature with respect to time, and it would be measured in degrees per minute. So what would it mean if I said the derivative has a maximum value of 4? Right, this is tricky. The maximum value of the derivative is telling you the fastest point where the temperature is changing. So if I say the maximum of the derivative is 4, that means when this soup's temperature is changing at its fastest, it's changing at a rate of 4 degrees per minute. What would make the soup's temperature change more or less quickly? Yeah, if you turn the temperature of the stove up, it's going to have a higher impact on the temperature of the soup. So another way to interpret that derivative is it's actually telling you about what the cook is doing, not necessarily what's happening in the soup. That was the original function. It tells you what happens in the soup. But if the cook turns up the stove, then the resulting temperature of the soup is going to change, and the derivative measures that change. So in some ways, you could think of the derivative as kind of giving us the cause that is behind the function. Let's put this in context with some numbers. Here's another example, and this one's about hiking. Take a moment to read the example, and then plot the data here on a simple graph. Now, I know you haven't read the example yet, but I want you to pay close attention to how your units should look for the y-axis. Go ahead and create your graph. Okay, here's what my graph looked like. And notice that I used units in thousands. This should have been intuitive to you because our elevation numbers are pretty high numbers, but keep in mind that this is going to affect the slope. If I go to this point right here, it's not the 0.11 anymore, it's the 0.11,000. So that's going to mean a really high slope if I were going to that point. I'm not though. Okay, next step, let's connect the dots to get a sense for what this hike really looked like. We get something like this. And if I were to tell the story of this hike, I would say, well, the hike started out at a pretty low altitude, and then the height or the elevation of our hike increased until we reached maybe a top or a summit. What would the derivative of this function represent? Exactly. So the derivative is the slope, and in this case, what the slope means is basically how steep the hike was. This point right here in the middle is really, really steep. In fact, you could think of the picture up here where these people have to even hold on to ropes. Down here at the beginning of the hike, the slope, or the derivative, is a smaller slope, which means it wasn't as steep. Well, what if we wanted to be even more precise? It looks like the steepest part of this graph is somewhere around 2 miles in. What if I wanted to actually estimate how steep the hike was at that point? What could I try? Exactly, I could try calculating a slope. Now, since I don't have grid lines, and this is just a graph that I drew myself, it's probably not going to be very easy just to estimate this line using points on the graph. So instead of just estimating randomly using my visual instincts, what if I were to take these two data points, which are from the table? What if I calculate the secant line between these 2 points? That would be probably a pretty good approximation for the tangent slope right here in between them. Here's what that would look like. First of all, I've switched graphs, but this is, notice, the same data. And I'm trying to find the tangent slope right there in red. I know that these points on either side are the points with these coordinates. And so I'm going to calculate the slope, delta y over delta x, and that's just a normal slope formula. When I do that, I get a slope of 2343.75, and it's measured in feet per miles. So we would say the steepest part of this hike is about 2 miles in, because that's the horizontal distance. And how steep is it? Well, it has a steepness of 2,343 feet per mile. It's a pretty steep hike. Let's take this one step further, and we'll do this with another example. The data below shows the depth of water in a puddle by the side of a road on various days last week. We're going to graph this data, and then we're going to graph the derivative of this data. And then we'll use the two graphs to A, explain what the weather was over the course of the week, and B, to understand what the derivative is really telling us. To start with, we want to basically just put this all on a graph, but we have a units problem. Graphing Monday 8 a.m. is not a very easy thing to put on an axis. We would put that on the x-axis. So instead of saying Monday 8 a.m. for my x value, I'm going to reinterpret this, and I'm allowed to do this as long as I stay consistent with all the units. I'm going to call Monday at 8 a.m. times 0. And then I'm going to measure in units of 24 hours what the next time was. So if Monday 8 a.m. is times 0, Monday at 8 p.m. is 12 hours later. In other words, it's a half of a day later. So Monday at 8 p.m. would be the number 0.5. And what I'm doing is I'm just measuring time in terms of days after Monday. When I go to create my graph, I'll label the x-axis that way, time measured in days after Monday. So go ahead and use this pattern to fill in what should the rest of the times be. You're going to need to reference the actual chart, so I'll put this back up for you. Here are the values that I got. Notice that I've got some funky decimals here. Tuesday at 4 p.m. is 8 hours after Tuesday at 8 a.m. Well, Tuesday at 8 a.m. would be exactly 1 day later. And then 8 hours after that would be a third of a day. That's where the 0.33 came from. Go ahead and graph this data. Adjust your values if you converted any of the decimals incorrectly. Great, here's what my graph looked like, and yours should be somewhat similar. Let's take a moment to make sure that we understand what this graph is really saying. Tell me, what would this point represent? Exactly, this is the maximum of the puddle graph. In other words, this is when the puddle is its deepest. It happens somewhere on the second day. Actually, if you think about it, this was Monday starting at 0, Tuesday starts at 1, so it's sometime on Wednesday that the puddle is deepest. How about, what does this point represent? Yeah, this is when the puddle is shallow again. I don't know if it's really the shallowest because it looked pretty shallow when we started. Now, what would the derivative of this graph represent? Exactly. The derivative would be the change in the depth with respect to time. In other words, we would measure the derivative in inches per day. And we would expect the derivative to be positive because the water is increasing at the beginning. And then we would expect the derivative to be 0 at this point, and then negative because the amount of water is decreasing again. Now, before we would estimate the graph of the derivative by sketching tangent lines. When you're creating your own graph, that's not very precise. So instead of that, what we're going to do is we're actually going to use the values in the table to estimate what the derivative should be on various intervals. Here's what I mean. We want to graph the derivative function. So we're going to take a number of times, and we're going to calculate the slope at each of those times using the table that we had. Remember the example from before? In this example, we estimated the slope at point 2 using 2 points on either side. We're going to do something really similar. You will need to remember the midpoint formula. If you don't, here it is. The midpoint halfway between two x values is x1 plus x2 divided by 2. So for example, my first 2 data points from the table were x values 0 and 0.5. Halfway between them would be the point 0.25, and I get that by adding and then dividing by 2. What I'm going to do is I'm going to calculate the midpoint slope using these 2 points. So I'm going to use the slope formula on the first 2 points, and I'm going to call that the slope of 0.25. Here's what it would look like. Graphically, this answer of 4 represents the slope approximately halfway between my first 2 data points. So right here, we're estimating that the slope is approximately 4. Is that a correct estimate? Well, it's an approximation. We can do the same thing. The next thing we would do is we would take a midpoint halfway between the next 2 data points. Numerically speaking, that would be halfway between 0.5 and 0.133. To get that number, I'm going to add 0.5 plus 1.33 and then divide by 2. That gives me an x value of 0.915. And then I'm going to use the next 2 points and the slope formula to calculate the slope at time 0.9. I'll continue this process, and eventually here's the table that I'll get. All of the x values in this table are still representing time. They're the midpoints of my original function's x values. All of the y values in this table represent rate of change, in particular change in depth divided by change in time. And I just got them using the slope formula with each of the pairs of numbers from the previous table. Take a moment to sketch these points. What graph do they create? Right, so here's what my graph looked like. And in fact, if we look at the bigger picture, and we look at the original function along with the derivative function, we'll start to see some familiar relationships. When the amount of water in the puddle is increasing, the derivative graph is a positive value. When the amount of water decreases, the derivative is a negative value, and then it increases again in the end. So let's pause. Looking at these 2 graphs, tell me what happened in the puddle over the course of the week. Be as specific as possible. On each day, what did the puddle look like? Okay, now tell me about the weather. What happened to the weather over the course of this week? So hopefully when you answered the first question, you looked at this first graph, because that's what this is really. This first graph is telling you about the puddle. It's saying that the puddle was shallow, then it got deep, and then it got shallow again, and then it got a little deeper. In order to answer the question about the weather, you needed to look at the derivative graph. Why would the puddle get deeper? Well, presumably because it's raining. As long as the y value is a positive number here, the weather must have been rainy, which means that it was then sunny down here because the puddle was drying out, which is why the depth decreased. I'm going to leave you with one last example. You'll do it on your own, and we'll talk in class.